So section 4.5 would be about the rational functions and their graphs. So we're going to take a look at how to find to define the definition of a rational function when it is a function rational, and how to find the domain, and we will take a look at the graphs of rational functions, and in particular, we will take a look at what we call asymptotes of a graph when it comes to graphing a rational function. So first, let's look at the definition of rational function. So all rational functions are functions that are given as a fraction of polynomials. So the top is if you have P of X and Q of X that are two polynomials, and then you define a function f of X where you divide P of X by Q of X, well, this is going to be called a rational function. Just like these examples, you can see a polynomial on top, one in the denominator, same thing here, and same thing here. So that said, well, actually, I'm going to want this to be 4 here. So 4. 4 here. Okay, never mind. So this can be 5. Okay, so we're gonna continue with that being 5. So the condition here is that you don't want to have a denominator that is 0, because in this case you would know that the function will not exist. So you always want to make sure that you don't have 0 in the denominator. So otherwise, that's the definition of a rational function. Now we're going to see how to find the domain of a rational function. Actually, we know how to do it. More practice on that. So you know, when you're looking for the domain of a function, you're going to look for where this function will exist. So for a rational function, it exists when the denominator is not 0. So that means the domain here will be for x squared minus 2x minus 8 not to be 0. We don't want it to be 0. If it's 0, then the expression will not exist. Otherwise, it's cool. So then that would be x minus 4 minus plus 4 times x minus 8, 2 equals 0. So x plus 4 equals 0, or x minus 2 equals 0. Well, not equal 0. That's a condition. We don't want those two to be 0, and in this case, it will be and. We want both of them not to be 0. And then, so we can subtract 4 on both sides. X is not equal to -4, and we can add 2 on both sides. X is not equal to 2. So the condition here, if you want it to be in set builder, notation, your domain will be all real numbers x such that x is not equal to negative 4 and 2. But most of the time, and in all time on you always want to know how to write your domain or your solution in interval notation. So your domain in interval notation would be from negative infinity to the smallest value, negative 4, union from the smallest value to the largest, and union from the largest value to infinity. Well, because we need to exclude negative 4 and 2, we always keep parentheses on them. So that's the first example. The example B, same condition. We don't want the denominator to be 0. So that's x cubed minus 5x not equal 0. We can factor the GCF, x squared minus 5x, x squared minus 5 should be not 0. So x cannot be 0. And x squared minus 5 cannot be 0. Well, if you solve, then that would be x not equal to square root of 5 plus or minus. So it's both of them, plus square root of 5 or minus square root of 5. So we have 3 values to exclude in the real numbers to find the domain. So the set builder notation for the domain is all real numbers except x 0 plus minus square root of 5. In interval notation, from negative infinity to the smallest value, square root of negative square root of 5, union negative square root of 5 to 0, union 0 to square root of 5, union square root of 5 to infinity. So that is the domain in interval notation. The last one is the same concept, C. You don't want the denominator to be 0, so that's 3x minus 15. We don't want it to be 0, so that means we don't want 3x if you add 15 to be, if you add 15 on both sides, we want 3x to be not equal to 15. If you divide by 3, we want x to not equal to 5. So your domain in set builder notation will be set of x of such that x is not equal to 5, or in interval notation, it will be from negative infinity to 5, union from 5 to infinity. And over here, we have more problems. I just solved them. You can just see how we did the previous ones, and then that'll be the same thing over here. We have another problem here. Same way, you just set the condition for the denominator not to be 0, and then present your domain in both set builder and interval notation. So in the next slide, we're gonna talk about what we call asymptotes. Well, You know, remember when we were talking earlier about the condition for the function to exist? The values that make the denominator equal 0 are excluded from the set of real numbers to define the domain of the function. Now we're going to talk about what we call vertical asymptote. A vertical asymptote of the graph of a function is the line x equals a, where the graph increases or decreases indefinitely when approaches to a. Well, this is a very fancy definition of the vertical asymptote, but really what you need to know is that for any value that is restricted from the domain of rational function, it creates an equation of vertical asymptote. So if a is one of the values restricted or if a makes the denominator of the rational function equals 0, then x equals a is a vertical asymptote. But the one thing that you need to make sure you know is that asymptotes are equations. Let me write this down. The reason I say asymptotes are equations, if 5 is a value that makes the denominator of a rational function equal 0, like when you replace x by 5 in the equation, the denominator is found equals 0, then x equals 5 is a vertical asymptote, not 5. 5 is a number, x equals 5 is an equation. So values that make denominator equal 0 create an equation, creates x equals that value to be an equation, or asymptote, to be the equation of a vertical asymptote. So that said, when you're looking for the domain of a rational function, you set denominator not equal 0, and you find the condition of existence of the function. And this condition is used to find the equation of the vertical asymptote. But we have to note that if a factor is common between the denominator and the numerator of the rational function, it reduces to 1 under the condition that this factor is not 0. Well, if I have a factor that is common under the condition with the numerator and denominator, under the condition that this factor is not 0, you can simplify it. In the language they often use, you cancel that factor. The reason I say cancel, it's not canceled. It equals to 1, and when 1 multiplies, it doesn't change the expression. So if you want to say it cancels out, yes, you can say it, but it reduces to 1. And now when it equals 1, you don't see it anymore because you're dealing with multiplication. But this is done only if the factor is not 0. And if you consider the value that would make this factor equal 0, then this would be called as a hole in the graph, a hole. But both holes and vertical asymptotes are restricted from the domain of a rational function. Well, this is a whole theory that we're talking about. We will do more examples for you to understand, but both holes and the and the vertical asymptote, both together, they are found when you find the values that are restricted from the domain. Also, we can talk about the horizontal asymptote. The horizontal asymptote is a line y equals b, where the graph approaches the line as the variable x approaches infinity. Well, increases indefinitely. If the graph approaches this line as x going up, going right indefinitely, or left indefinitely, then you know that you have a vertical asymptote. Well, you have a horizontal asymptote, but if it's y equals a constant, and then you're gonna talk about a slant asymptote, we're not going to break down in this class if the line is if it's a linear equation. So if it's a linear equation with a slope equals, if a slope m not equals 0. We're not going to talk much about slant asymptote in this class, so that's why you can, well, you can identify whether you have you're going to know how to identify where you have a slope, where you have a slant asymptote. Well, let's say instead, in this class, the focus will be vertical asymptote and horizontal asymptote. Now, if you don't have a horizontal asymptote, you're gonna say no, you don't have it, or when you have it, you can calculate it. Now, how to determine it, the vertical asymptote. Now, to determine it, to find the vertical asymptote, what you do is you need to solve the denominator equals 0, and then all the values you get will constitute an equation for your vertical asymptote. So let's find the vertical asymptote for each of the functions. Determine the equation of vertical asymptotes of the graph for each of the following functions. You start it the same way. Start with the bottom of the rational function equals 0. So that's x squared minus 2x minus 8 equals 0. Wherever it's 0, whatever the x value that makes it equal 0, we create an equation of your vertical asymptote. So we can factor this: x minus 4 times x plus 2 equals 0, x minus 4 equals 0, or x plus 2 equals 0. Add 4, x equals 4. Subtract 2, x equals negative 2. So x equals 2 and x equals negative 4 are the vertical asymptote for this function. So vertical asymptote are x equals 4, not 4, x equals 4, and then x equals negative 2 are the equations of your vertical asymptotes. Next, we can do this one. So now, one thing you need to make sure when you're doing that, you need to make sure that when this expression is factored, the top expression cannot be simplified. If it can be simplified, you should do it. I'm looking at the bottom expression here. Let's try to factor this. So f of x will be x minus 2 over x times x squared minus 4, which is also x minus 2 over x minus 2, x plus 2. Now you can see how x minus 2 is coming from denominator and numerator. Well, that means you can simplify by this. Well, when you simplify, that doesn't mean that it's gonna disappear your function. Obviously, your function became a new function, but it creates at x equals, well, the zeros of the denominator are gonna be x equals 0, x equals x minus 2 equals 0, x equals 2, x plus 2 equals 0, so that's x equals negative 2. Well, for x equals 2, that's the factor that you canceled out, right? So your new function is now 1 over x times x plus 2. X plus 2. But that doesn't mean that the x minus 2 disappears and you have nothing left for it. Well, what happens in this case is that the vertical asymptotes are x equals 0 and x equals negative 2. And then at x equals, you got a hole at x equals 2. Have a hole at x equals 2, and those are your vertical asymptotes. And then the last one in C, example C, let me erase this. In C, you're going to do the same thing. Take the denominator. Let me write in a different color here. So you're going to take 3x minus 15 equals 0. And you add 15 on both sides. 3x equals 15. Divide by 3. You get x equals 5 is your vertical asymptote, because the top factor would not simplify. Let's see if it would simplify. If we factor, nah, no way. Well, no, it would not simplify. Okay. Now, how do we find vertical asymptotes? I mean, horizontal asymptotes. Horizontal asymptotes are, to find them, you have 3 conditions here to when you're looking for whether you have existence of vertical of horizontal asymptote or what is it. Well, the first condition is to verify if we call n the degree of the numerator and d the degree of the denominator. Well, if degree of the numerator is less than the degree of the denominator, if n less than d, that means you have a higher degree in denominator, then your equation of the horizontal asymptote is y equals 0, not x, y. Y equals 0. If you have the same degree both in numerator and denominator, the equation of your horizontal asymptote is y equals the ratio of numerator leading coefficient and denominator leading coefficient. And last, if your degree in numerator is greater than the degree in denominator, you have a possibility of a slant asymptote. But with what it's clear, you do not have a vertical asymptote or horizontal asymptote. You do not have a horizontal asymptote. Now, degree of the, what do we get here? Do we get a degree that is greater in numerator or less? Well, it's less. So the degree of the denominator is bigger than the degree of the numerator. So we get, because numerator degree is 1 and degree in denominator is 2. So we have degree in numerator less than degree in denominator. So you have y equals 0 is your horizontal asymptote. That's A. In B, let's see what happens. We got the same situation happens. You have the same situation. So y equals 0. For this one, it reverses, right? You got the degree in N is 2, degree in D is 1. So N, that's the last condition, is greater than D. So no HA. Now let me take another example. If I give you f of x equals 2x squared minus 5x plus 1 over x squared plus 5x minus 2. We have this, and I want you to find the the equation of the vertical of the horizontal asymptote. Same question here. Same question here. So because d n equals 2, d equals 2, so we have n equals d, then the horizontal asymptote will be y equals the ratio of the coefficient of the numerator in coefficient of the leading coefficient of the numerator is 2 over the leading coefficient of the denominator, that's 1. So HA is 2. So we have three conditions. One, where the degree of the denominator is less than of the numerator is less than the degree of the denominator. If the degree of the denominator is less than the degree, if the degree of the numerator is less than degree of the denominator, the horizontal asymptote equation is y equals 0. So that's why this one, n equals 1, and then d equals 3, n less than 3, n less than d. That's why you have this. Y equals 0 is the equation of the horizontal asymptote. If the degree of the numerator is greater than degree of the denominator, you have no horizontal asymptote. And if you have the same degree, you calculate the ratio of the leading coefficient in numerator over the leading coefficient in denominator to get the equation y equals this ratio to be your horizontal asymptote. So that's if you get the equation of the function. Now let's see if the graph is given to you. Now, when the graph is given to you, the lines where the line passes through determines the equation of your asymptotes. Now, this is the graph of a rational function. And then they want you to find from this graph the equation of the asymptotes, the horizontal asymptote and the vertical asymptote. Well, x equals 4 is the line, is the value, x value that this dotted line passes through. But also we can see how the function is, right? The function increases indefinitely as x approaches this value. As the value of x is getting closer and closer to 4, as x is moving towards 4, the graph is getting closer and closer to this line. But as x is getting closer and closer to this function, that's what I meant, and the graph is increasing indefinitely. It's going up. And you would not expect the graph to touch this line. It will keep going all the way up. Now, if you consider the graph going, the x value approaches 4 from the left, well, you would see the graph that is going indefinitely down, never touches this line. So that makes the x equals 4 what we call a vertical asymptote. Well, it will never touch it, but when the graph is approaching, when x is getting closer and closer to 4, the value x equals 4, we see that the intention of the graph is to go up or to go down indefinitely. So that makes x equals 4 on the graph the equation of your vertical asymptote. So x equals 4 is the equation of the vertical asymptote. Now we're going to look for the equation of the horizontal asymptote. Now, as x approaches, as the graph approaches the line indefinitely, as the line, this line, you already see what value it is. So we see that x, as x approaches infinity, so because let's see, x is moving this way, that's negative infinity. The more the graph, the x is going to infinity, the more this line is getting closer and closer to the line y equals 4. And then when x is going this way, see, and then we see the graph is getting closer and closer to the line y equals 4. So that makes the line, the horizontal asymptote, that is going to be y equals, is it negative 4? It's negative. So the concept of asymptote, vertical or horizontal, is the fact that sometimes you see the graph tends to increase or decrease indefinitely as x is getting closer and closer to a certain value. If the graph tends to increase or decrease when the x value is approaching a certain given value, then this certain value will be called x equals that value, a vertical asymptote. Now, when the graph approaches a certain y value, when x heads toward negative infinity or positive infinity, that means the more you get big values, the more you see the graph is approaching that y value, then y equals this value would be called a horizontal asymptote. So that's why we have this in this y equals negative 4 here, because we see the graph getting closer and closer to that line y equals negative 4 when x is heading to a positive infinity. But from the bottom, you see how the graph is getting closer and closer to the same line as x, as you getting lower and lower value for x. So then that makes a conclusion, y equals this value would be called a horizontal asymptote. So all this talking we were saying, so it's basically to say that x equals 4 is your vertical centered, y equals -4 is your horizontal centered, and the domain here, domain will be everything except the value x that x equals to be the vertical centered. So that means it's all real numbers except x equals 4 would be the domain. So all real numbers except domain. Except 4 in interval notation will be negative infinity 4 union 4 infinity. And then they may ask you for the range also. The range will be all real numbers except the value y equals 2, that is your the range is all real numbers except the value y, the value of y that makes the horizontal center -4. So that's negative infinity, -4, union -4, infinity in this case. They didn't ask me for it, but in case you are asked for it, that's what you're gonna give. All right, so in this case, they ask me to analyze the graph of f of x equals 2x minus 4. First, by finding the domain, find the vertical asymptote or asymptotes, if any holes, the horizontal asymptote or asymptotes, the x and the y intercepts. So let's go ahead and find the domain. Domain will be all the values for which the denominator is not equal to 0. So x minus 4 should not be 0. So x equals 4 would be the excluded value for which we don't want to, we cannot have. So that's the value we cannot have for x for the existence of the function. So domain will be from negative infinity to 4 union 4 to infinity. And they ask in the next question, what is the equation of the vertical, or equations of the vertical asymptote? Well, the same value x equals 4 you excluded from the domain will be the equation of your vertical asymptote. And if you had two values excluded, and you would have two equations, two vertical asymptote equation. Any hole, well, we didn't cancel any factor, so no holes. The horizontal asymptote. Horizontal asymptote would be whether you have 0 if the degree of the numerator is less than the degree of the denominator. If degree of, well, let me call n the degree of the numerator. If it's less than degree of the denominator, HA is y equals 0. If n equals d, y is the ratio of the leading coefficient in the denominator and denominator. And then if n is greater than d, then you have no HA. In this case, degrees are the same. The ratio would be, the second condition would be kept because degree one here. So the equation of your horizontal asymptote will be y equals the ratio. The leading coefficient in numerator is 2. Leading coefficient in denominator is 1. So y equals 2 would be the equation of your horizontal asymptote. X-intercept. Well, x-intercept is when f of x equals 0. That's when f of x, y equals f of x equals 0. So that means your f of x, 2x over x minus 4 is equal 0. It's like 0 over 1. You can cross multiply to get 2x equals 0 times the denominator, x minus 4, which is still 0. So 2x equals 0. Divide by 2, x equals 0. So that means you have x equals 0 and y equals 0 because you had it here. So that's 0, 0, which would be your x-intercept. Now, how do you find y-intercept? Y-intercept is when x equals 0. So y-intercept is found. Y-intercept is found when x equals 0. Well, x equals 0, that means y will be f of 0. So you replace x by 0, 2 times 0 over 0 minus 4, which is 0 over -4, which is 0. So also y-intercept is x equals 0 and y equals 0. Now, in order to graph your rational function, you may want to find some particular values or some spatial values for your function. So what you can do is you can, because the domain of the function, we're not going to forget it's from -infinity to 4 and union from 4 to infinity. So I'm going to try to make sure I'm very strategic when I'm looking for the values, because I need to get some values from each piece of the domain so I can clearly see how the function is, the pattern of the function from the domain over the domain. So that's why I'm gonna look for some values here and some values here. So from -infinity to -4 to 4, I can take, I guess I can take 5. X equals 5. X equals, let me take x equals, because I don't want values that would be negative, values that will give me fractions, because fractions is hard to find on the number line. So that's why I always look for values that are integers, easy to find on the number line. So okay, okay, one thing you can do is you can use your graphing calculator to find table. So let's see how we can use the graphing calculator to do that. See, all right, so that's your, all right, try to make sure you can see that. Uh, Not sure you can see, but I'm gonna try my best. So the graphing calculator, you type your function. See, we type this function here. That's your function was 2x. Let me find my fraction, math, and then over to the left, after math, over to the left, and then I get my fraction. Now, the fraction here, I'm going to type the numerator of the function, that's 2x, 2, and then the x theta, x theta, xt theta n is the x for me, and then move it to the bottom. If you click on the right arrow, it moves it to the bottom for you, and then you type x minus 4. Now, if you look at the graph button on top of it, it says table. When you do second function and then the graph button, it gives you a table. So second, and then, oops. I don't need the graph, I need the table. So second, go back to graph. Second, and then table. Now it gives me that table. I'm looking for best values that I need. I see -4 give me -1, so I'm gonna use -1. I'm gonna use -1, so -4. Oops. -4 is -1. And then let me keep going down to see what I see here. Well, 0, we always need 0. 0 is 0. And then let me see what else I can find. I see 2. 2 is still on the left side. Let me take negative now in 3. 3 is -6. And then I'm gonna need a value in this because all these are on the left side or on the left side. Now I want some values on the right, so I'm gonna take let me see 5, 6, all of them that can work. So let me take 6. 6 is also 6. So those values can help me find a pattern for the function, and then that can help when you're graphing the function. Now, after you find the values, you can use the graphing calculator and try to see how the graph looks to see which one you would pick, because most of the time, mostly if you are taking your test online, they would not ask you to sketch a graph. But if you're not taking the test online, if you're taking it on paper, you might be asked to find to actually manually sketch your graph. So now that you have your domain, well, you have your spatial point. You can go and identify which graph it is, but it's also that you can hit the graph button and then you would see which graph corresponds to your function. Then I see that the one that is closer to be the function that I see in the graphing calculator is B, because I found a vertical asymptote to be 4, and that's what I see here. And then that's my horizontal asymptote. And also the points that I found, -4, -1, x equals -4, y equals x equals -4, x equals was, let me see, -4. Oh, -4 is +1. So it's -4, +1. So -4, +1. So that is this. Um, 0, 0. That fits. 3, -6, x equals 3, y equals -6 also fit. Then you could just connect to sketch your graph. And then on the other side, we had 6, 6, x equals 6, y equals 6. And then you would, I mean, 1 point is hard, but you know that you're gonna connect the dots if you want more. Let's see, all of them would be fractions. We had 8, right? Let me see, 8. X equals 8 is 4. X equals 8, y equals 4, and then you can just connect the dots to get the graph here. So that's if you sketching your graph, your graph manually. Now, the next example here, we're going to do the same thing, but the only difference now is that we see that the degree of the numerator is less than the degree of the denominator. And also, you can see how the denominator can be factored as, well, the top is the same, but it's a squared minus b squared. So that's x plus 1, x minus 1. So the domain will be x plus 1 times x minus 1 equals 0, not equal 0. So x plus 1 not equal 0, or and x minus 1 not equal 0. So x cannot be -1 and x cannot be +1. So your domain will be from -infinity to positive, to -1, union from -1 to 1, and then from 1 to infinity. That's your domain. And then the equations of your vertical asymptote will be pretty much the same equations you had from the domain, but it's not going to be not equal. It's going to be x equals -1 and x equals +1. That these are the equations of your vertical asymptote. Now, did we simplify any factor? No, we did not. So we have no holes. We have no holes. And then the horizontal asymptote, because the degree of the denominator, the numerator is less than degree of the denominator, you would note that the equation of your horizontal asymptote is y equals 0. X-intercept will be when f of x equals 0. X-intercept is when f of x equals 0. F of x equals 0, which means y equals 0, right? Which means y equals 0. So f of x, we know it's 2x over x squared minus 1. That is 0. So cross multiply would get 2x equals 0. Divide by 2. We get x equals 0. We have x 0 and y 0. Y-intercept is when x is 0. So in this case, y will be f of 0, right? So you plug in 0 for x in f of x. 2 times 0 over 0 squared minus 1. So that is y equals 0. So also y-intercept will be x equals 0, y equals 0. We're gonna do the same thing here for finding some specific points. Domain is from negative infinity to -1. If I put 0 here, +1, and then infinity. So we need some values here, some other values between -1 and 1 other than 0. We can stay with 0 only, but we do need some values in here too from 1 and infinity. So I'm gonna put 0 here, 0, 0, and then some specific values that we can use to find the pattern of the function. I'm gonna take some fractions in this one, unfortunately. So -3. I found them by using the same trick I showed you in the graphing calculator. -3, that -3, -3/4. That will be over here. We already have 0. We got 2 4/3, and then 3 4 3/4. But you can calculate them, so you can just plug in those values and find what the y values are. So once you get that, and then you can identify the graphs, let's see if which graph would first. Let's identify the asymptotes, -1, 1, and y equals 0. -1, 1, and y equals 0. Well, all of them give me the same. Well, this one is not y equals 0 because y equals -2 in this one. This one, y equals +2. It can't be a solution. So the solutions are possibly this one or this one. So now I'm gonna check with the values that I have here to see which one will give me. So let me start with clearly the 0 works for both of them. So I need to find something else to verify. Let me see x equals -3. I expect a negative solution, right? X equals -3. I expect a negative solution, -y. X equals -3. So it gives me a -y. So which make me feel like, well, it looks like, and for x equals -3 here, it gives me a positive solution, and I expected a negative, so D is not the solution. So I select my B as the solution. So basically, when you're looking for the graph, selecting your graph, you first use the asymptotes to see which one you can cancel. If nothing you can cancel, then you're gonna use the table of special values that you got in order to decide which graph corresponds to your function. So that's this for this question. for this next problem, this is your function. We are looking for the same questions. We were answering the same questions, but with a different function. So let me write this in a different in order. So negative 3x squared over x squared minus 4. So that's pretty much what we have here. First, I see that n is the same as d, like the degree of the numerator is the same as the degree of the denominator. So that means the horizontal asymptote will be 0. So let me go ahead and answer that question quickly. The horizontal asymptote, the equation of the horizontal asymptote will be y equals 0. Also, the other thing that I can see, there's no way that I can cancel a factor here. So I also see that there will be no holes here. Domain will be, because this is x squared minus 4, so I can factor this as x squared minus 4 should be not equal 0. That means x plus 4 times 2. X plus 2, because we factor this x squared, 4 squared is 2. 4 is 2 squared. So that's why so x squared minus 4 is x squared minus 2 squared, which is a squared minus b squared formula, x a plus b times a minus b. So that's x plus 2, x minus 2. Okay, so that's why I have this x plus 2x minus 2 here. Equals 0. Now, well, not equal 0, meaning that x plus 2 is not equal 0, and x minus 2 is not equal 0. X is not equal to negative 2, and x is not equal to 2. Your domain will be from negative infinity to negative 2, not included. Negative 2 to 2, we're not including none of them. Union 2 to infinity. And those two values restricted from the domain will constitute the equations of the vertical asymptotes. So that's x equals negative 2 and x equals positive 2 for the equations. We already said that this function has no hole, and we saw because the numerator degree is equal to the denominator. No. Well, the numerator degree is the same. Well, that means we need to have the ratio. Y equals the ratio of the leading coefficients. I'm sorry I put 0, but it's not going to be 0. Leading coefficient in top is negative 3. Leading coefficient in denominator is 1. So the equation of the horizontal asymptote will be negative 3 over 1, which is just negative 3. So we use the ratio. So now we can find the x-intercept. X-intercept is when you set y, which is f of x equals 0. That would give me negative 3x squared over x squared minus 4 equals 0. So that is negative 3x squared equals 0. Divide by negative 3. X squared equals 0. Square root of 0 is 0. So that means x equals 0. X equals 0. Y equals 0. So 0, 0. Y-intercept y-intercept will be when x equals 0. So in this case, y will be f of 0. Plugging in 0 for x for 0, 0 replaces x in the equation, -3 times 0 over 0 squared minus 4 is y. So that means y equals denominator 0 over -4. I mean, numerator 0 over -4. So y equals 0. Also, the y-intercept is x equals 0, y equals 0. So I'm going to use this in my table as well, 0, 0. And then I'm going to need values between all the intervals of my domain, from -infinity to x equals -2, with 0 here, x equals 2, and then infinity. So we already have 0 between -2 and 2. That's fine. I need some values here too. Let's see which one we can get. So you can use your graphing calculator to find those values too. So I have -4, -4. I have -1. Let me put 0 here. -1. -1 is 1. So this is already between -2 and 2. And then the last one, I'm gonna take it here, which is 4. 4 is negative. So I have those values. First, to get the graph, I'm gonna try to identify the asymptotes. What's the vertical asymptotes are -2 and +2. So all of the asymptotes are -2 and +2. They can help me. But now let me look for the horizontal asymptote. The horizontal asymptote is -3. Let me see which one does not have a horizontal asymptote. That's -3. Not -3, because it's +3 right here. So not -3. This one is -3. So this one is -3, can be the solution. This one is not -3, so it cannot be the solution. So it's either C or D. Now let me use the points that I have here to sort out one of them. -4, -4. -4, -4. X equals -4. Y equals -1. So this one is not. So let me see if this one works. -4. X equals -4, y equals -4. So this one is already didn't work for the first point. So the only one that's left is D. So D is my answer.